This turntable is using a tiny needlepoint to read the grooves on the vinyl and convert it to music. This is similar to how a scanning tunneling microscope in STM works, but the STM reads bumps and grooves on the atomic scale using quantum tunneling. Let's break it down. To start, imagine a ball. This ball represents an electron. The ball's possible position is not fixed. Instead, it can be represented by a wave function. The function is continuous and shows the probability that the ball could be in different locations. But what if there was a barrier that the ball does not have enough kinetic energy to pass through? Classically, the ball could simply not go through the barrier. But because the wave function is continuous, the probability cannot immediately drop to zero. Instead, it decreases quickly and exponentially. So, if the barrier is thin enough, the probability of the function may extend into the forbidden region. Because of this small probability, some electrons may move through the barrier. This movement through the barrier is called quantum tunneling. A key component of tunneling when applied to an STM is the size of the barrier. The larger the barrier, the smaller the probability of an electron passing through is. Going back to the turntable analogy, the record represents our sample being studied under the microscope, and the needle is the tiny metal wire tip used by an STM. By applying electric voltage to the needle or record, we can monitor the current of electrons passing through the space between them. This space is the barrier. Because the probability of electrons passing through the barrier is smaller for a larger barrier, by measuring the tunneling current of electrons, we can create a topographical map of the record. For an STM, the result is an extremely precise image of the surface, even down to individual atoms.